next Thursday. And it's going to be, I think, a Q&A. I don't know if any of you guys are members of that Phi Theta Kappa, but they're the folks who are bringing them here. All right, so I debated, but actually I want to kind of keep going in order. We need to talk about mixtures. And it shouldn't be too bad, because actually we've been kind of talking about mixtures. I'll show you this flow chart here of, like, if something is matter, how do you classify it, okay? And so actually we said it can be either a pure substance or a mixture right off the bat. All matter is made up of atoms, okay? And that matter, that chunk of matter you have, can either be pure. Okay. Now, if it's pure, we talked about actually you have two options. You can actually have all of the atoms of the same type, and that's an element, okay? If it is, basically, we talked recently about how atoms join together in repeating units in a compound, either ionic compound or molecular compound. Okay, that would also be a pure substance. Okay, so those are examples of pure substances. I have a homework assignment coming up that's due Friday, you know what I mean? It's due Friday. And it actually asks you, how do you go back and forth between elements and compounds? And the answer here is you have to have some sort of chemical reaction. Okay. So if we compare that to mixtures, okay? Mixture is a mixture, and I have some examples of mixtures coming up here. But mixtures can either be the same throughout, we call those homogeneous mixtures, or they can be chunky. I call it chunky. Okay? Chunky is a heterogeneous mixture. And the thing about mixtures is basically you have just physically tossed the two things together. So this says if you have a mixture and you're like, dude, I don't want a mixture, I want a pure substance, then all you got to do is some sort of physical process to get your piles of pure substances back. Okay. All right. So a couple examples of mixtures down here in these beakers. Now, if I were to say that this is, let's look at the first beaker. I mean, if I say it's mostly water, you're saying like, oh my gosh, there's some blue in there. Just the fact that you see a blue color means that it's water contaminated with something that's blue. Okay. So that means that there's two or more substances in there, at least two substances in there, okay? And the fact that you can't kind of differentiate between the water and the blue dye, I mean, it's all the same throughout. So this is an example of a homogeneous mixture, okay? Homogeneous mixture. Then over here, again, if we just kind of like visually look at that kind of sandy looking stuff, you're like, I see black, I see, tan, I see kind of a darker tan. The fact that it's chunky, it's not the same throughout, that's a heterogeneous mixture. And honestly, if you had enough patience with this heterogeneous mixture, you could start a pile of black stuff, a pile of this color of sand, You could try to separate it out into its individual pure substances if you wanted to, piles of pure substances. This one right here, let's just say that it's Kool-Aid, okay? Right? Yeah, and you could actually get back your little Kool-Aid particles if you evaporated it, okay? We just like drove off all the water. We could separate it back out into the water, which is most of it, and the little residue, which is like your Kool-Aid stuff. That evaporation actually is a physical process. So we can kind of get back to what we want there. As we're breathing air, and I think I might have mentioned it, it'll come up in meteorology, okay? But just regular old air is mostly nitrogen and some oxygen. Remember we talked about those diatomic elements the other day, the Hofbräu nickel. Okay, of course, nitrogen is a diatomic element. Okay, so that's the two cute little atoms of nitrogen running around, and it's about 20% oxygen. And this is actually showing you a sea, where actually this down here, these cute, anytime you see something that looks like kind of like that, like a Mickey Mouse sort of thing, that is your water molecule. And we actually talked the other day how, of course, water is H2O. Okay, so water has an oxygen atom and two hydrogens. And so the white things are the hydrogen atoms. Okay. So anyway, so we have water. We have actually this right here, the pluses and minuses. That's like table salt dissolved in water. Okay, so of course seawater is very salty, and so what happens is you have Na plus and Cl minus running around in there. That's your pluses and minuses. So it's definitely a mixture, probably homogeneous, but. So the thing about mixtures is that the pure substances themselves get to retain their identity. It's kind of like, I haven't thought about this stuff, but supposedly when you get married, you retain your own identity, right? Okay, you are the same person. So these things are the same things. But one thing about it is, and this wouldn't, I think the whole marriage analogy kind of falls apart here, but you get to pick, like the substances you want to make a mixture out of, you get to pick what sort of ratio you want them to be in, okay? So depending upon kind of how you choose them to be a certain ratio, okay, then that whole mixture can have certain properties depending upon how you chose to mix the two pure substances. So an example I like to choose is again Kool-Aid, and our youngest is now 16. I can't believe it. But so when she used to make Kool-Aid, she used to make it like it says like 1 cup of sugar. She would like put 1.5 cups of sugar. Okay. So Kool-Aid is basically water with sugar and the little Kool-Aid. Okay, but it's mostly water and sugar. Okay. So in her case, she chose to have a certain ratio of water and sugar. In my case, I'm kind of liking it on the tart side, so it's like even 3/4 of a cup of sugar, you know. So we made up 2 different mixtures with different, you know, tangy properties or sugary properties. So again, so how do you take a mixture and go ahead and break it back down into its pure substances? Now, it's got to be some sort of physical means, and I kind of circle that. You know, take a mixture, break it down into pure substances by some sort of physical properties. Sometimes it's easier than others. Literally picking out like those pieces of sand, that's a physical process. Okay, evaporation is also a physical process. All right. So, the term solution, there's a lot of S's in the term solution. Well, there's one S in the term solution. But by definition, solution is an example of a mixture that's the same throughout. Okay? So a solution is an example of a homogeneous mixture. In solution science, right, you basically have a solute and a solvent in solutions. Oh my gosh, too many S's, like I said. Okay? If you're into like reworking wood, like refinishing furniture, you go out and you get furniture, you get the remover. Okay, sometimes they call that solvent. Okay, to prepare your stuff so you can stain it or paint it. So solvent actually is there in greater amount. So water is a great solvent, and I think it's not the only solvent, okay? But the stuff that's there in a greater amount is called the solvent. The stuff you sprinkle in or you add in, okay, is called the solute. Okay, so I just kind of picture those things. Solvent and the solute. So water isn't always the solvent. Water's not always the solvent, but it's a good one. A lot of things dissolve in water, not everything. Okay? If water is the solvent, then the solution we have is we call an aqueous solution. And actually on the next part, and I think actually when we did our copper lab this week, remember anytime you see AQ, okay, that means that basically it's running around in a bunch of water. So water is the solvent. Okay, so solutions. Solutions are a type of homogeneous mixture. So by definition, what a mixture is you have two things that you are submitting to occupy nearly, they're in close proximity. That's what a mixture is. Now, I want to kind of talk you through these options with regard to your solution. Your solution can be what we call unsaturated, and I have an example coming up here in a minute. But unsaturated just simply means that you could, if you wanted to, you could add more of the stuff you're adding to your solvent. You could add more solute. It's unsaturated. I go back to my daughter making up her Kool-Aid. Okay? When I make up the Kool-Aid, I would have my water ready and I'd add 3/4 cup of sugar. I would stir it up. I don't know, sometimes it takes longer than others, but I stir it up kind of depending on the temperature, right? I'd stir it up and all my sugar would go into solution. Okay, all my sugar would dissolve. It would all dissolve. Okay, could I add another 1/4 cup and would it dissolve? Yeah. Okay, that is an example of an unsaturated solution. It just means I can add more solute. That's it. Okay. I take my daughter's example. Okay. So here's the deal. When she adds 1.5 cups of sugar, maybe if she's patient enough, it will all go into solution. Maybe all of that sugar would dissolve into water, into one big homogeneous solution. So we have the water and the sugar all went away. It's all dissolved. Maybe. But I tell you, if she tries to add 1 more cup of sugar, an entire cup, so that brings it up, what, 2.5 cups? Okay? You're like, dude, she can stir and everything. She might need to heat it. She can stir and everything, but she's going to get a sludge at the bottom there. Okay? That is actually what we call a saturated solution. She can try to add more sugar, which is the solute, but, you know, not more of it's going to dissolve. Basically, it bumps up to what we call kind of a capacity of that solvent to dissolve the solute. Okay? So solubility is kind of that capacity. So we aren't going to do much with numbers, but I'm going to kind of show you some numbers. So solubility basically is how much solute can I shove into a given amount of usually solvent? How much can I dissolve? How much can I dissolve? Okay. I mentioned temperature. It is depending upon temperature. Okay. In general, if you heat it up, more of it's going to go into solution. Okay. So that's solubility. Supersaturated. I always think of supercalifragilisticexpialidocious, right? Supersaturated is actually, I'm going to try to show you in kind of a non-animated description of supersaturated. But supersaturated, and it happens in physical science. Supersaturation is a player when it snows. Okay, who likes the snow? Well, that's supersaturation. Okay. So supersaturated just simply means that for whatever reason, you have gone beyond kind of the known amount that should be soluble at a given point. Basically, you're over the solubility amount, okay? And you can get there if you're careful and kind of some certain conditions. That's supersaturated. Okay, so unsaturated. Here's an example. Notice we've got a little 30 grams of NaCl. That's going to be our solute. And we have 100 milliliters of water waiting to go ahead and dissolve it. Notice there's no sludge at the bottom there, okay? I don't have the example to show you, but just by the picture, we're like, hey, that must have all gone into solution. So that's an unsaturated solution. Then we compare that to this, okay? Where instead of 30 grams, we're going to up it to 40 grams. Now, there are numbers here. Like I said, you can look it up into a table. Those solubility tables would be specific for the solute and actually the solvent. If you're going to dissolve salt, NaCl, into H2O, you have a certain limit. And actually, it's not much, but can you see that cute little sludge over there? Okay, in the bottom, there is the sludge. It's not much, okay? But as much as they want to stir it at that given temperature, that certain amount is not going to dissolve. But here's the catch. It does dissolve. So anytime you dissolve something, okay, this is actually trying to show you the dissolving process, where down here, this is your solid, okay, and right here This is your stuff that's dissolved. It's what we call a dynamic process, that basically some dissolves, some kind of comes back into a solid. Some dissolves, some comes back into a solid. They're like switching up who gets to be in solution, who gets to be a solid. It goes back and forth. But it has a constant amount of sludge at the bottom. So what looks static, what looks not changing is actually dynamic. Okay, so I mentioned temperature dependency. So here's a figure from your textbook. Okay, so the way you read this, and we haven't done much with graphs in here, but the way you read this, and let's find NaCl. Really? I don't see it on there. I see a bunch of, what's that? Do you see it? Okay, let's pick something else. Let's pick KCl. That's about as good as we can do. So you're like, K is, of course, potassium. So instead of sodium chloride, this is potassium chloride. And let's go ahead and pick, for instance, 20 degrees Celsius. Okay, so this whole line, this whole purple line is potassium chloride. Let's go ahead and pick a temperature of 20 degrees Celsius. Okay, and the way you do this graph is you go up here, and where it intersects, okay, actually go over here, okay, and that actually is the solubility in grams of KCl, that would dissolve in 100 grams of water. Okay, so that's kind of the tipping point for KCl at that temperature. So that's how that kind of works. Notice that if we go ahead and jack up the temperature to, let's go with boiling. Okay, water boils at 100 degrees Celsius. Okay, notice then we can go over here to right here at 100 degrees Celsius, and we go back over here and pick up its solubility. And so let's just gonna go ahead and do that. I get, let's see, degree 20, 20, 40, maybe, gosh, 58. I'm gonna go ahead and call it 58. It's almost to 60. 58 grams of KCl per 100 grams of H2O, right there at 100 degrees Celsius. I'll pick green, and over here, I'll go ahead and call that, I'm liking maybe 40, let's go with 40. That to me kind of looks like a 40. So that means 40 grams of KCl per 100 grams of H2O at 20 degrees. So, of course, 58, it's more soluble. You can put more KCl in at a higher temperature than you can at a lower temperature. So it usually increases with temperature, not always. You see any up there that actually decrease with temperature? Increasing temperature and its solubility goes down? This weird one right here, this cerium sulfate. Yep, it goes down. And there is a reason for that. All right. So I said I'd have like a still image of supersaturated. If you've ever, and I used to have one of these in my lab, but they have these like, they're hot pads, they're heating pads. And basically you activate the heating pad by kind of flexing it. I don't know if you've ever run into those. And actually it's probably something like this. Sodium acetate is great that if the pack that you buy is basically supersaturated sodium acetate solution. Okay? When you flex it, you're basically disturbing that supersaturated solution. Anything super doesn't want to stay the way it is. Okay, so supersaturated, it wants to come out of solution. When it comes out of solution, it's what we call very exothermic. It gives a lot of heat. So anyway, kind of from left to right, what they're doing here is disturbing a supersaturated solution by seeding it, looks like, with a little grain of salt. Okay, so kind of from left to right, basically, you see it basically come out of solution. Okay, it was supersaturated here. Okay, they disturbed it. And it comes out of solution. Pretty cool. So we have unsaturated, saturated, and supersaturated. Well, let's go on and talk about chemical reactions. Oh, wait a minute. There's a assignment slide. Sorry. So assignment slide, page 330. Short answer. Numbers 3, 5, 6, and 7. And then on page 331, exercise number 2. And I don't have like a hint slide per se, but thank you. I don't have a hint slide per se, but you recognize the figure that I brought in. So that figure actually for sure will help you with exercise number 2, and it will probably help you with the other ones. Okay. So those are for sure due Friday. Let me get my days straightened out. So these are due Friday. Now remember that the sheet I gave you with the compounds, either Friday or Monday. So it's up to you. I think you'll do fine with the sheet of ionic compounds, but due Friday. Does it feel like midterm is coming up? Yes. It is. No. Whew. We've been at this a little while. Okay? Very good. Just dabbling in chemistry. And tomorrow, when we dabble in pHs, okay, the whole chemistry of pH, actually, I don't get to the chemistry of pH until I have like general chemistry 2, so it's like second semester chemistry. But I think we'll know enough to kind of talk just kind of at the top of what pH is and what pH isn't maybe tomorrow. And it's kind of fun because tomorrow, actually, when we do lab, you guys are going to use the lab quests again, and it's pretty straightforward. You stick the little dippy thing in your fluid, and it tells you what the pH of the solution is. But you're also going to use red cabbage. I don't know if anyone likes red cabbage in here. So you're actually going to do something you could do at home. We're going to use I'm going to extract red cabbage juice, and you're going to use that to like visually look at what the pH would be. So it's kind of fun. She's like, oh, I think it smells already. Red cabbage. It'll be okay. I'll do it, like I said, I think this time I'm going to prep it ahead, so you guys don't have to prep it. But I really feel like last week when you guys did your copper lab, thank you for not blowing up the lab. Yes. Good job, guys. And not having any major like issues. I don't know if anybody's fingers turned. Mine kind of felt slimy. I don't know if the sodium hydroxide makes you feel slimy. But good job. So a lot of chemical reactions last Thursday. So what a chemical reaction is basically, this talks about the nuclei. Now, what is the nuclei? And I meant to bring my BBs, okay, but yeah, the nucleus. The nuclei is like plural for nucleus. Okay, so one nucleus, several nuclei, right? So basically, they're the center of atoms that are home to your protons and your neutrons, okay? When a chemical reaction occurs, that stays intact, totally intact. When an ordinary chemical reaction occurs, and that's all we're worried about. But what does do some kind of scrambling are those electrons. So when the electrons actually rearrange themselves on what we call the product side. So we looked last Thursday at a lot of chemical equations. So an equation is like a sentence. So an equation in general is read from left to right. This is like your equation, okay? Left to right. You start with your reactants and you end with your products. This is what you start with, and this is what you end with. Okay? And the point here is that if I make these little green, I'll make 5 green ones. Those are the nuclei. Those are the centers of my atoms. I'll make 5 green ones and 2 blue ones. Okay? If that's what I start with, okay, then actually what I should end up with are 5 green ones, 5 green ones, and 2 blue ones. Okay, those are my nuclei. Okay, so that's all that means. Chemical reactions, the centers that you start with are the centers that you end with. I always think of like a Tootsie Roll, you know. I went out and bought like one of those $10 things of like the candy, and I've been eating it ever since. Like October and Halloween is evil. So anyway, okay. So there you go. It is. So again, I refer you to what you guys experienced in the lab on Thursday. You did a lot of observations and writing down, okay? And actually went ahead and your instructions told you what the chemical reaction was, okay? So a lot of times, not always, but a lot of times you can actually visually see that something's going on. Other times, it's a way of seeing it, but actually the catch with this little picture is that these, I'll put clear liquid, clear, the letter L for liquid. Actually, these are both clear liquids. These are two things that are going to react. Two clear liquids minding their own business. When you let the two clear liquids come in contact, you get actually a solid that's formed. That little white fluffy stuff is a solid. Two clear liquids give you a solid. So you're like, oh my gosh, well, if I got a solid, that's an indication that something happened. Another way you can know that something happened, in Thursday's lab, remember some of the parts you needed to go under the hood to do your thing, okay? Some fizzing. Anytime you see fizzing, of course, you're creating, I'll put the letter G for gas. Okay, you're creating a gas. Okay, so that's a new substance that wasn't there before. This is actually just showing you somebody's, looks like a stove, doesn't it? Like a stovetop. Somebody's got gas for their stove, and they're just maybe going to heat something up, and they have their gas burner burning. So this example here, now not always, because some things can release heat and they are not a chemical reaction. But this actually, you probably know that you are taking some sort of fuel, fossil fuel, you're taking gas, okay, and you are burning it. I'll put an arrow, and over my arrow I'm going to put the word burn, okay? And actually, as you maybe know, when you burn fossil fuels, you get carbon dioxide, which is in the news. I'll put a G next to carbon dioxide. And you also get water, H2O. Oh my gosh. The movie The Martian, he made his own water by burning. So anyway, there you go. So that is a chemical reaction. Heat is released, but sometimes heat is released and it's not a chemical reaction. Here's one of those glow sticks, right? The emission of light can be an example of chemical change going on. Again, not always. Light is a type of energy, though, isn't it? So, all right. So, in Thursday's lab that you guys did, you did all sorts of chemical reactions, and for each chemical reaction, I gave you the equation, the chemical equation for the reaction. Okay. Now, I don't know if you don't have to pull them up if you don't want to. But all of those, actually, those equations that I gave you, all of those equations actually were balanced. All of those equations were balanced. And we'll talk about balancing. I'm kind of coming to a close of how far I wanted to get today. We'll talk more about balancing on Friday. Okay, but they were all balanced. But I also want to kind of, on Friday, emphasize what you get by an unbalanced chemical equation. Balanced and unbalanced. Nuts and bolts of it is that, well, I think I'll just kind of, I'll take a running start at this topic on Friday, okay? All right, so we're done early, and it's Wednesday.